Welcome back to Aerospace and Mechanical Lab 2. As you're aware, one of the things you need to do for the vibration lab is to actually find the roots of this function for the free beam and then roots of this function for the cantilever beam. These are huge functions. You can really solve them by hand, and I'm going to show you how to write a MATLAB code that will help you find the roots of these two functions. As an example, we are only going to do the free beam vibration code, and then you can use the same method, same analysis, same everything essentially to find the cantilever beam vibration roots. First of all, we need to understand what each part of the equation is. This x hat of n as a function of x is the normal displacement, so the amplitude of your function, essentially this movement, the actual vibration that is happening right in this direction. X is the location you are on the beam. So let's say this is your 1 meter beam, goes from 0 to 1. This is normalized length, so x divided by L. X is going to tell us where we are on the beam, and for each location, using that function for each mode of vibration, we can find out what will be the maximum normal displacement that our beam is going to see at that specific point. Okay, so maximum normal displacement at any point, at any x, is equal to hyperbolic cosine of beta n multiplied by L multiplied by x divided by L plus cosine of beta and L multiplied by x over L and the rest of the function. So to find the node points, we essentially are looking for points where this value is 0. We're looking for x's that are going to give us the value of xn of 0. How can we do this in MATLAB? Okay. I've already written the code in MATLAB, so I'm just going to write it again with you and try to explain as much as possible. If you have not used MATLAB before, you can just follow me and copy whatever I'm doing. You just have to change your function for the cantilever beam analysis. But our assumption is that you have already passed your numerical methods course and CSC 206 or CSC 206, so you have a basic understanding of MATLAB and Python programming. Okay, so the first thing you want to do when you're writing a MATLAB script, for our case, is that you want to clear the previous data. So we're going to start with the command CLC and clear, and we are going to close everything that was open from previous runs. Okay, so for this code, let's go back to the PowerPoint. In this code, the length of our beam is a constant value that doesn't really change. So 1 meter beam, usually in some cases your beam's length is actually smaller a little bit, like 98 centimeters, 97 centimeters, but for this code I'm just going to use the 1 essentially. So length of the beam is equals to 1. This, then I'm going to comment this as well, length of the beam. Okay, this is the first thing we have defined. The next thing we want to define is to actually our function, the mode function, the displacement function. Let's call it the mode shape function. Okay, so I'm going to define it like this. I'm going to call my function mode shape. This is just a name, and then this is equal to, the first thing you want to do when you are defining a function is you have to define your variables. Our variables are x and beta n L. Like whenever you see in this equation, beta n and L are always together. So we're just going to lump them together. The reason is you're also given the values for beta n, beta L. These are the roots of the characteristics function. You don't really need to know what these are, but we just essentially have to use the three first values for our analysis. Okay. So I'm going to define beta and L as one variable. Why is this a variable and not a constant? Because we are trying to graph three different modes of vibration. So this is going to have three different values. So this means that it is actually a variable. And then the other thing that can vary in this function is the length of the beam itself. As I said, it is usually kept at 1 meter for our experiments, but sometimes it's smaller and bigger. What was the function? Function is cosine hyperbolic. This is the cantilever beam function. Cosine hyperbolic beta and L xl plus cosine beta and L xl and minus the rest of it. I'm just going to write the first parts, which was cosine hyperbolic and then beta and L multiplied by x divided by L. This is adding this by cosine of the same thing essentially. So I'm just going to copy and paste the insides of this cosine hyperbolic. And then we want to continue to writing the code minus the other things that we have. We want to continue writing this code in the next line. So I'm just going to use these three dots and then go to the next line. What do we have here? We have cosine hyperbolic beta and L minus cosine beta and L divided by sine of the same thing, sine hyperbolic minus sine. So we have, to start with the parentheses, cosine hyperbolic beta and L, right? This is minus cosine beta and L. And all of this is divided by I've put everything in a parenthesis. All of this is divided by the sine function. As you can see, I have a dot and then the division. This is referring to the element division in functions. We don't want to divide arrays. We want to make sure that it is just dividing the two numbers with each other. Okay, so this is how you define a function in general. We are going to get in the numerator, we are going to get sine of hyperbolic of the same thing minus regular sine of same thing. Okay, and then there is another parenthesis. All of this is multiplied by, again, dot multiplication, multiplied by, let's go back to the lecture notes, sine hyperbolic beta and L xl plus sine of beta and L xl. You can go to the next line again. So sine, I have to remove this excess from my equation, and also else because of how it was defined. Okay. Sine hyperbolic of beta and L x L minus plus, I'm sorry, plus sine of same thing, and then the parentheses must be close. And then at the end of this, you want to make sure that we have a semicolon to tell the MATLAB that this is our function. Let's double check the function together. We have a function of x, beta and L that is equal to hyperbolic cosine of beta and L multiplied by x divided by L plus beta and L, cosine of beta and L multiplied by x divided by L minus this whole thing, which is essentially just a constant for each mode of vibration, and this is multiplied by the hyperbolic and regular sine. Okay, I think we are ready to move forward. So the other thing we want to do is to define beta. Beta and L, we are given the values in the lecture notes, so we don't really need to do any calculations for this. But this is, we are going to define this as a vector with 3 values because we want to do the first 3 modes of vibration. What are the 3 values? We can go to the lecture notes and find it in a table. The first one is this. I'm just going to use 4.73. Second one is 7.85. And the third one is 10.99. Okay. So 4.73, 7.85, and so I forgot the comma, 7.85 and 10.99. This is our beta values. What about the x values? So x values is essentially a continuous part of the function that goes from 0 to the length of the beam, right? But we can't really define it as a continuous thing. For our purposes here, we essentially have to define x values. I'm going to define it as x value, and I'm going to define it as line space of 0 to L and 1000. So essentially this command is going to create a vector that has 1000 values between 0 and L, and these values are evenly spaced. They have the same space. So essentially we go from 0 to 1000s, 2000s, 3000s, and up till until it gets to 1. So essentially we have 0 values. We are evaluating this for 0 values in our 1000 values in our x direction. So the next thing we want to do, we want to create a vector that can record our roots. I'm going to call this roots list, and this is essentially just a cell that in one direction has the length of the beta and L, and in the other direction is only 1. Okay. Okay. So for the next step, I am going to create a loop in which we are going to take these betas, beta and L's, and find the roots of this function for each beta and L. Essentially, find the roots of the function for each mode of vibration. So our for loop has to go from 1 to the length of beta and L. So essentially just 1, 2, 3 in this specific scenario, but we don't want to limit ourselves to our specific scenario as much as possible. So I'm going to write my for loop as for I starting from 1, and it has to go 1 by 1 to the length of beta and L. And then I'm going to define a variable inside this loop called, let's call it beta, and that is equal to beta and L of I, which essentially means that if I is equals to 1, this value of beta is going to be equal to the first value in the beta and L vector, which is 4.73. Is the value of beta and L for the first mode of vibration. Okay. And then I'm going to define a root function that is a function of x and is essentially its function is equals to the mode shape function that we had previously, where x is given as an input and beta and L are our constants that go in there. See, so we are passing through just one beta and one L, and these two are defined. One here, which is L, is essentially just always a constant for this function, for this specific code. And then within the loop, we are just passing one beta to this function. So the only variable for us is x in this root function. Okay, we are planning to use the F0 library in MATLAB to find the roots of the function. And if you recall from your Euler methods of finding the roots of the function from the numerical methods course, we usually need to start with some guesses. So what we are going to do is we are going to provide 10 guesses for value of x. Now this is the value of, this is our goal, to find the value of x. And then we are going to pass each of these 10 guesses to our F0 and then compare the results with the previous guess. And so this is a trial and error. And then as long as the accuracy meets our standards, we are going to spit that number out as the actual root of the function. Okay, so what should I do here to use the root 0? I have to define root guesses. So my guesses for the root, initial guesses that are going to be passing through. And this is going to be a vector. I want to pass 10 guesses, let's say. We already know that my guesses are between 0 and L because the value of x is always between 0 and L. And I need 10 values. These are 10 guesses that I'm going to pass to my F0 function. And then I am going to define a new array that mode shape function roots that can actually has a dynamic size and can store my calculated roots. So what is the next step? Again, we want to use this F0, but we have 10 guesses for the roots. So we have to write another for loop that goes from 1 to the length of my root guesses. So length of root guess. Okay. Let's actually, we should change this to J, I'm sorry, because we already have an I here. Okay. So now we are ready to pass this f0, to pass our essentially root function to f0 library. When I say f0, and the things we need to pass the function, we need to pass the initial guess and any options that we want to pass. We don't really have any options, but we just want to pass our function, which is the root function. Okay, and we want to pass our guesses, which are the root guesses. Right, these two, we don't really have an option here. And you have to keep in mind that the root guess does change, does take 10 different values. So it is a vector, but we want to only pass one variable. Sorry. Okay. So this is my f0, and then we have to set this equal to a root variable, whatever you want to call it. Just gonna call it root. You can call it A, B, C, and whatever, right? But the problem with this is that we are not actually, we don't have a stuff for accuracy analysis. So it just takes one of these guesses inside of this function and spits out another value for roots. And we don't really want this to happen. For example, we don't want our roots to be smaller than 0 or larger than L, right? So we need to actually come up with a methodology to check for this. We can use the if command, but there's another command in MATLAB. It's called the try and catch. So essentially, it is going to try solving this root, and then it is going to check whether our criteria is met. What is our criteria? We are going to define the criteria as this. We want root to be larger than 0. We also want it to be smaller than L. We also want the difference between this calculated root and the absolute value of the other roots, essentially the subtractions, to be smaller than a set value. It can be any set value, right? This is essentially where we are defining our accuracy of root calculations. So I'm just going to take the absolute value here of this calculated root with any root that is already stored in my root array. So mode root. Okay, this is, and we want this to be smaller than, let's say, 0.0001. This is my level of accuracy that I require from this. But the problem is, it only checks this root, cross-checks it with one of the roots that is calculated. And for mode 3 of vibrations, we are going to have 4 roots. So I'm going to add an any function here, tilde any, and then I'm going to put the whole thing inside the parentheses. So we'll actually go through all of the roots that are calculated. This is my if function, and then if this is the case, I'm just going to store the new roots. So mode root is going to be equal to whatever previous value I have stored here and I'm just going to add the new one to the whole list. Okay, and this is the end of our form. So the idea of try and catch is if this wasn't true, the code is not going to break. It will just go to the catch command and do whatever we tell it in the catch command, which is continue. So we are telling it to continue with the for loop. And then this is where we end the try and catch. This is also where we end this for loop for root calculations. The only for loop that is still open is the main for loop. For this one, we want to store whatever mode we have calculated in this root list that we have already defined. So we're just going to say roots list and I this refers to my beta value here, so the first mode of vibration, or we actually have to use accolades here, is equal to mode roots. We also want to make sure that this is sorted, so it goes from 0 value closest to the 0 to 1. So sort of mode roots. And then we can just finish the for loop. This is how we calculate all of the roots. Next step is to display these roots in this console. How do we display the roots? And now we are going to write another for loop. For loop again goes from I to I1 to the length of the root list this time. Okay. And then the function print command for us is fprintf for MATLAB. In the fprintf, we wanted to write first of all that mode. It's going to write the mode, and then we are going to ask this to give us the number of the mode. This is number 1, number 2, number 3 there. And then we want it to end the line. Okay, this is the first thing. You don't really need to write any of this. This is for educational purposes. Then we'll publish the mode of vibration at that specific or the line that is looking at, and then we want to publish the root list, but we want to publish it as a string, not as numbers. So we are going to use this function which changes your mathematical values to strings and root list of I. Sounds like all of these are done. This should do the job for us. Okay, just one issue is that I'm defining this as a root list. It should be roots list. That is where the error is coming from. And this is also roots list. I'm not sure why it didn't give us an error. And this is mode root. This should be fine. Okay, so if we hit run, I'm not sure if the program is gonna work because it's my first time writing this. If we run this, we should actually get all of the x values of interest for us. Let's see. Yes, so it's telling me that in line 16, I'm instead of a line, a space, I've written line spave, which is not correct. Let's see. Okay, so line 40. These things happen in programming. Just have to length. Oh, I'm sorry, length. Yep. So the program ran, but it's not publishing any of our roots for some reason. I'm going to stop this and debug the program, see where my issue is. Okay, I figured out what the problem is. I'm sorry for the hold. I was using a small, what did it do? I was using a small letter L here. I should have used a capital letter L. And this should fix the problem. Okay, so when you run this, we'll give you the mode 1 root. This is where this comes into play, mode 1 root, and this is the space between root and the rest of it, and these are the mode 1 roots calculated. So you want to compare these to your experimental values and see if these are closer to the experimental values compared to the values that you have calculated for the cantilever. You need to also include the mode shapes in your code. So for the mode shapes, we want to do this, plot this in a figure. So we are just going to create a figure, and we want to make sure that it is holding the figure for us as long as we're telling it. We want the colors to be red, blue, and green. So I'm just going to define this vector array as R, G, and blue. We're going to use this later in our graph. Okay, so we want to have 3 graphs on top of each other. That's why we have the whole line. We have 3 different shapes, so which essentially means that we need to have another for loop. So for, again, 3 mode shapes, so we are going from 1 to the length of my beta values. I equals to 1 to the length of beta and L. And then we are going to define the y-axis as the mode shape function. So y value is defined as the mode shape function. And the variables we are passing to this are the x values, which we have defined earlier. And then the beta and L's and the length of the beam. So next step is to actually plot this graph using the plot command. We want to have plot x and y, which is plot x values and y values. Sorry, y values. And then we are going to use the color that we have created, the color array we have created, and ask to use the first array of this color vector as the color for the first mode shape. So the first mode shape is going to have a red color. The second one is going to have a green color, and the third one is going to have a blue color. And then for the name, we are going to use the command display name. Yeah. And we are going to use it to print the mode number using the s print f of the, you remember how we did the mode number, mode %d and I, which is the first mode number for us. And that is it. Just a semicolon, and you end the for loop. We can also change the X label and Y label names. X label, we can name the X label as X, just call it X. And the Y label can be named as, let's call this normal displacement. Sorry if the spelling is wrong. I think there's an E here, right? We can also give a title to our graph, just mode shapes for free beam. And we can also ask it to show a legend, which essentially is going to tell us which color is what. And then we can have the grid, so we can better understand the graph. Let's see if we can actually see the graphs. I think I've made another mistake. It says error in line 48 right here. And it is telling me that this is erroneous. We have to use element-wise multiplication. Let's see if that fixes the problem. So here and here, and I guess here and here, right? Run again. I'm gonna stop the video again and see what the problem is. Okay, I'm back again. This is the issue. I forgot to refer to a specific array in the beta NL vector. So if you run this is what you're gonna get. You're gonna get the mode shapes. This is something that you want to make sure you include in your lecture notes, lab reports. And these are the roots that we wanted to find. I'm going to ask you to write the MATLAB code for the cantilever beam yourself, and I'm going to leave this video. I can put this video on Blackboard for your use.